We have talked about the difference between nonpolar covalent, polar covalent, and ionic bonds in an earlier chapter. We assign bonds to one of these three categories, either by what type of atom makes up the bond, or by calculating electronegativity differences. I mentioned that we needed some cutoff values for the electronegativity differences because there is no sharp divide between the three categories. Instead, it is a continuum ranging from nonpolar covalent, a complete sharing of electrons, to ionic, a complete transfer of electrons. We are going to do some calculations with dipoles and ionic character as another way to categorize where along the continuum a bond would lie. First of all, if our compound is ionic, we have individual charges and can use Coulomb's law to tell us how strong of an attractive force exists between the ions. Coulomb's law tells us that the attractive force is proportional to the product of the two charges divided by the square of the distance between the charges. Since the charges are in the numerator, the higher the charge, the more the attraction. For example, a +2 ion will be attracted to a -2 ion much more strongly than a +1 and a -1. Since the distance is in the denominator, the larger the distance, the less attractive force there will be. Ions that are closer together have more attraction. The smaller the ionic radius of each ion, the closer together the ions will be, and the more attractive force will exist. Another way that you might see Coulomb's law written is using energy instead of force. In that case, the denominator only has d instead of d squared. The examples given show that an ion with small charges and a larger distance will have significantly less attractive force than an ion with large charges and a smaller distance. For polar covalent bonds, the dipole moment is used to calculate how polar the bond is. The larger the dipole moment, the more polar the bond. Dipole moment, expressed with the Greek letter mu, is calculated by multiplying the magnitude of the charge, q, by the distance between the charges, r. Dipole moment is typically expressed in units of dBi, d. As we calculate the dipole moment, we will need to use the conversion factor that 1 dBi is equal to 3.336 times 10 to the minus 30 Coulomb meters. The dipole moment for hydrogen chloride is 1.08 dBi, whereas the dipole moment for hydrogen iodide is 0.44 dBi. These values are not the same as the values for their electronegativity differences, but they follow the same trend. Chlorine has an electronegativity value of 3.0, iodine has an electronegativity value of 2.5, and hydrogen has an electronegativity value of 2.1. Since chlorine is more electronegative than iodine, the electronegativity difference between hydrogen and chlorine, a value of 0.9, is larger than the electronegativity difference between hydrogen and iodine, a value of 0.4. This corresponds with HCl having a larger dipole moment. We can compare an experimentally measured dipole to what the dipole would be if the bond were completely ionic, the far end of our continuum, in which the electron is completely transferred. The result will be the partial ionic character, or how close to being ionic a bond is. The closer to 1, or 100%, the number is, the more ionic the bond. To calculate the partial ionic character, we will divide the experimentally measured dipole by a theoretical dipole calculated using the equation mu equals q times r. Here's an example of how we can do calculations involving dipole moments. The most important thing with this type of problem is making sure the units are correct. In this problem, we are told that the bond length is 0.127 nanometers, and the experimentally determined dipole is 1.03 dBi. Our first step in solving this problem is to calculate the theoretical dipole for if the bond were completely ionic. We will use the charge of an electron for Q and the bond length in meters for R. The units will end up being Coulomb meters, so we will need to convert from coulomb meters to dBi. Once we have our theoretical dipole in dBi, then we will calculate a percent ionic character and partial charges by taking our experimental dipole of 1.03 dBi and dividing by our calculated theoretical dipole. The charge on the electron would have to be given to you, and it is expressed in units of coulombs. Since we have a conversion factor which converts between dBi and coulomb meters, we need our answer to be in coulomb meters. We already have coulombs for our charge, but we need to get our distance r into meters. We convert 0.127 nanometers into meters and get 1.27 times 10 to the minus 10 meters. Once we have our charge in coulombs and distance in meters, we can multiply them together and get 2.03 times 10 to the minus 29 coulomb meters. Once we have our dipole moment in coulomb meters, we convert to dBi using a conversion factor, which again would be given to you in the problem. Just make sure that the units cancel out properly. We come out with 6.09 dBi for the value of the dipole if the electron were completely transferred. To find the partial ionic character, we take the 1.03 dBi experimental dipole, which was given to us in the problem, and divide by our calculated 6.09 dBi dipole. We come out with 0.17, or in other words, 17%. Essentially, 17% of an electron is transferred from the hydrogen to the chlorine. The partial charge on each of the atoms could be expressed as plus 0.17 on the hydrogen and negative 0.17 on the chlorine. What is the partial ionic character of Hi, which has a dipole moment of 0.42 dBi and a bond length of 0.161 nanometers? The charge on one electron is 1.60218 times 10 to the minus 19 coulombs, and 1 dBi is equal to 3.336 times 10 to the minus 30 coulomb meters. Is the answer A, 6.8%, B, 26%, C, 770%, or D, 5.4%? The correct answer is D, 5.4%. First, we use the equation mu equals Q times R. We plug in the charge of one electron for Q and the bond length in meters for R. The bond length is given to us in nanometers, so first we have to convert it into meters. When we plug those into our equation, we get 2.58 times 10 to the minus 29 coulomb meters. That is the theoretical dipole moment if the bond were fully ionic. We convert it into dBi by dividing by 3.336 times 10 to the minus 30 and come out with 7.73 dBi. That is still the theoretical dipole moment, but it is in a unit that we can compare to the experimentally measured value given to us in the problem. To find partial ionic character, we take the experimental value of 0.42 dBi and divide by our calculated theoretical value of 7.73 dBi and come out with 0.054, or in other words, 5.4%.